Greetings and welcome to Chapter 7, the Central Limit Theorem. In this lesson, 7.1, we're going to cover the Central Limit Theorem for the sample means. Get to know the new terminology for this lesson. Click on each of the words, learn its definition and meaning. When you are ready, click Continue. The central limit theorem is one of the most powerful ideas in statistics. Now, I know that's very easy to say in terms of, just willy-nilly I can say this, but it really is. The central limit theorem allows me to take any population distribution, no matter what it looks like. It could be a uniform distribution. It could be an exponential distribution. It could be a distribution that doesn't even have a name. And I can take that distribution and morph it into a normal distribution. The power in that is we know a lot about a normal distribution. A different distribution that doesn't have a name or we have not studied doesn't have a lot of information for us, but if we can morph that into something that we do know a lot about, that's very powerful. And the central limit theorem allows us to do that. There are a couple of wordings for central limit theorem. One wording is if we collect samples of n size with large enough n to calculate each of the sample mean and create a histogram out of those means, then the resulting histogram will tend to have a normal shape, a normal curve. So it doesn't even matter what your population distribution looked like. If you take large enough samples, take those samples means, that shape will be a bell-shaped curve. The second wording is, again, if we collect samples of size n that are quote-unquote large enough, if we calculate the sum of each sample and then create a histogram of those sums, that again will have a normal shape, a normal bell curve. And again, it didn't matter what the population distribution looked like. That's pretty powerful. So we can anticipate what a distribution will look like in terms of its sample averages or the sample sums. So here's the idea about central limit theorem. It says if we keep drawing larger and larger samples, such as rolling 1, 2, 4, or finally 10 dice, and then calculating their means, the sample mean will form their own normal distribution. The normal distribution will have the same mean as the original distribution, and it will have the same variance as the original variance divided by the sample size. And you can extend that to the standard deviation, because square root of the variance is the standard deviation, and therefore you can extend that idea out to the standard deviation. Now let's take an experiment. I have a bag full of dice, and we'll say there are a total of 50 dice in the bag. And I decide I am going to roll one dice 100 times, but every time I pull out a dice, I'm going to roll it. I'm going to record value of that dice, and then I'm going to put the dice back in the bag, and I'm going to pull out another random dice and roll it. If I do that 100 times and I record how many ones pop up, how many twos pop up, how many threes pop up, what you'll see is it looks like a uniform distribution. Well, I only rolled one die, and it would make sense that every single value, every single 1, 2, 3, 4, 5, 6 on that die has an equal shot at being rolled. Now, instead, I'm going to pull out 2 dice, and I'm going to take the average of the value of that dice. So I'm going to add the 2 dice values together and divide by 2, and that will be my average of the dice value. And I do this 100 times, and every time I put my hand in the bag, pull out 2 dice and I roll it. I record what the average is. I put those 2 dice back in the bag. I pull out 2 new dice and I roll it. I calculate that average. I put that back in the bag and I do this 100 times. You'll see that lo and behold, I will eventually get something that looks kind of like a pyramid. Not quite normal, but now let's try it with 4 die. Okay, so I put my hand in the bag and I pull out 4 dice and I roll those 4 dice. And again, I take the average value of the 4 dice. I add up all the values that come up on the dice and I divide by 4. Pick up the dice, put them back in the bag, pull out 4 new dice, roll those and record it again. And lo and behold, when I make a histogram of all that data, it's starting to look more and more normal. Now this time, I'm going to pull out 10 dice at a time, roll all 10 dice, add up all the values of the 10 dice, and take the average of it by divided by 10, and I'm going to record those averages. And I'm going to do this 100 times. So I put my hand in the bag, pull out 10 dice, and roll those dice. Add up all the values, divide by 10, record it, and put the dice back in the bag. After I do that 100 times, I'm going to build a histogram out of that data. And lo and behold, you'll see even more so. It looks more and more like a normal curve. That's what central limit theorem is all about. The larger the n, my sample size. So when I was 1 dice, it didn't look much like a normal curve. Even when I was 2 dice, it didn't look too much like a normal curve, but it is starting to form that peak. With 4 dice, even more so, and 10 dice, it's really starting to look like a normal curve. Now, if my n is large enough, it will form this bell-shaped normal distribution. Like always, it's very important that we talk the same language in math. So let's talk about the notation and the math function notation as we go through the sampling distribution. I do want to stress that although the notation is changing, the math really isn't changing. Look past the subscripts that you're going to see, and you'll see the same math that we have been using. So don't freak out that it's a new notation and think that you have to learn new math. You're really not learning new math, it's just new notation. So the normal distribution of the sample means has a notation like this. Capital X bar is the normal function, and it takes 2 arguments. It's the mean of the population x's and the standard deviation of the population x's, all divided by the square root of n. So anytime you see a little subscript of an x, it's talking about the population. Anytime you see a subscript of an x bar, it's going to be talking about the sample means. Now the sample means does have a mean, right? We take all the sample means and then we take the mean of that stuff. That's going to equal the population mean. So mu sub x bar will equal our mu sub x. The mean of the sample means equals the population mean. The variance. The variance of the sample means equals the variance of the population divided by n. So remember, anytime you see an x bar, that's talking about the sample means. Anytime you see an x, that's talking about the population. The standard deviation is just the square root of the variance. So taking the square root of both sides of the variance, you get the standard deviation of your sample means. So sigma subscript x bar equals our sigma x all divided by the square root of n. And our z-scores that correspond with the sample mean is going to be z equals x bar minus mu sub x, remember that's the mean population, all divided by sigma sub x all divided by square root of n. Now really that sigma x divided by square root of n is the standard deviation for the sample mean. So you could replace the denominator with sigma x bar. Let's work through an example by hand. An unknown distribution has a mean of 90. When we're faced with an unknown distribution for the population, we really want to use Central Limit Theorem to do this problem. Because we don't know the behind-the-scene shape of our population, we can't say that it's uniform or geometric or exponential. We don't know. So using the Central Limit Theorem is really going to be our key here. So an unknown distribution has a mean of 90 and a standard deviation of 15. Using samples of size n equaling 25, we draw randomly from the population. Let's first find the probability that the sample mean is in between 85 and 92. The first thing we need to do is calculate the mean for the sample means. Well, that's super easy. We're going to assume our mu sub x bar equals our mu sub x, and therefore it's 90. Our population has a mean of 90. Our mean of the sample means is also going to equal 90. Second step, let's calculate the standard deviation for the sample means. Now, if we remember, the standard deviation of the sample means is the standard deviation of the population divided by the square root of n. So our standard deviation of population is 15. Our n is 25. We're going to take the square root of 25, which is 5. 15 divided by 5 is 3. We didn't even need a calculator for that. So for the first two steps, we know that our mean for our sample means is 90, and our standard deviation of the sample means is 3. Step number 3, we need to calculate our z-scores for 85 and 92. So for 85, our x bar is 85, our mu sub x is 90 because it's the same thing as our sample means, and it's all divided by our standard deviation of our sample means. We've already done that work of standard deviation of the population divided by the square root of n, so we might as well use our standard deviation of x bar. So z equals 85 minus 90, all divided by 3. We get negative 1.6667, rounding. For 92, we have 92 minus 90, all divided by 3, which is 0.667. Step number 4, I need to translate my z-scores into p-values. The p-value for a z-score of negative 1.6667, I'm just going to go out there on the web and use one of the p-calculators. I get 0.047787. For the z-score of 0.6667, I get the p-value of 0.7475181. Now, final step is I've got to answer this question. Step 5, let's figure out the probability that the sample mean is between 85 and 92, meaning I'm going to take the p-value corresponding with 92 minus the p-value corresponding with 85. And we get 0.6997311, and rounding that to 4 decimals, we know the probability that our x bar value is between 85 and 92 is 0.6997. What if we want to know what the value is that's 2 standard deviations above the expected value of 90 of the sample mean? Now, it sounds very, very complicated, but we've done this before. Giving us 2 standard deviations above, that's our z-value. And we know our x equals mu plus z sigma. But in this case, our x is x bar. Our mu is mu sub x. And our sigma is our sigma x all divided by the square root of n. Plugging in these values, mu sub x is 90. Z is 2, because we're 2 standard deviations above, so it's a positive 2. Our sigma x is 15. Our square root of n is the square root of 25. We know that 15 divided by the square root of 25 is 3. So 90 plus 2 times 3 is 96. So the value that's 2 standard deviations above the expected value of 90 is 96. There are quite a few websites out there that can calculate the normal cumulative density function, which is what we're looking for when we're looking for probability. So I did find one that seems very reputable. It's from Stanford University. So here's what you would do. You would just put in your value, and our value was 92 for our high value. Our mu is 90, and our standard deviation was 3, and it will calculate it for us behind the scenes. So the probability that the value is 90, given that our mu is 90 and our standard deviation is 3, is 0.7475. Now, we will have to do a little bit of math after this, but this is just getting those probabilities pretty quickly. Our next value was 85. All the rest remains the same, and I'm going to hit calculate it. And this one was 0.0478. Now to find the probability that our values are in between those two, I'm going to take the 0.7475 and subtract the 0.0478. And that you can just use a calculator. So I'm just going to pull up my calculator here. And 0.7475 minus 0.40478. And I get the 0.6997. So I did have to do a little bit of calculator work after the fact, but the hard work of really translating it over to a z and then a p is all done using this website, normal curve density function. I'll add this website into our Canvas area, but I just wanted to show you kind of live how to work with this particular calculator. When using the TI-84 Plus for normal distribution and Central Limit Theorem, we're going to use normalcdf generally. I'm going to go ahead and graph the normal curve for this particular problem, but we are going to need the mean for the sample means and the standard deviation for the sample means to be able to plot the correct point. Now I will say I've already adjusted my window. My window is going to have a minimum of 1.75, the maximum of 2.25. It's going to be a scale of 1 for the x's. The y is going to be a minimum of negative 0.1, and the y max is going to be 6. Our scale for the y is 1, and I'm going to leave the other items alone. Now, how did I figure out these values? Remember, using the empirical rule, that 99.7% of my data falls within 3 standard deviations below and 3 standard deviations above the mean. Now, the mean is 2 hours, and the standard deviation is 0.5, but that's for our population. We want for our mean happens to be the same for sample means. So our sample means equals our mean for our population. Now our standard deviation for the sample means is going to be our standard deviation divided by the square root of n. Now I don't have to calculate this. I'm going to just throw it into to plot the actual curve, the PDF. I'm going to use normalPDF. So second distribution, normalPDF. My x value is just going to be some x values, but I do need my mean of 2 and my standard deviation of 0.5 divided by the square root of 50. I'm not even going to have to calculate it. It's a calculator. It will calculate it for me. I'm going to go ahead and paste it in Y1, and I'm going to graph it just so you can see that the normal curve is indeed a normal bell curve. Now that we have our normal bell curve, I want to know what is the probability that sample means is between 1.8 hours and 2.3 hours. Now, I could just throw it into the CDF function. So I could say second vars normalCDF, but I actually want to draw it. And since it's draw, I'm going to shade the norm. And I'm going to go ahead and put in my values. My lower boundary is 1.8. My upper boundary is 2.3. My mean is the 2. And the standard deviation is the 0.5 divided by, not alpha, our second square root of 50. I am going to color it green so you can see the difference. The curve itself is not going to be different. The bell shape is not going to be different, but you'll be able to see it draw in a different color. And I'm going to go ahead and click on draw. There's our normal, and it is filling it in. You're probably going, oh my gosh, it's filling in everything. Well, wait until you see the probability. The probability is 0.9977. So yeah, almost the whole entire curve is shaded in. Now, what would be the sample mean for the 84th percentile? In this case, I know what my percentile is. It's 84%, and I need to know how many hours is that. That means I'm going to be working backwards. So I'm not going to graph this. I'm just going to go to second distribution, and I'm going to go to inverse norm. So 3. My area is 0.84. My mean is 2. And my standard deviation is going to be the 0.5 divided by the square root of 50. And therefore, it would be 2.0703 hours. That would be the 84th percentile. So to graph, I use the normal PDF. To shade in my graph, I used ShadeNorm, and it also told me the probability. And then to find if I already know my percentile, to find the actual sample mean, I would use my inverse norm, invNorm. But what if I didn't want to graph it, and I wanted to go straight to what is the probability that sample mean is between two values? Then I would say second bars, and I can go to normalCDF. My lower, I just put in the same values as I do before. Upper, 2.3. Mean is 2. And my standard deviation is 0.5 divided by the square root of 50. And this just won't draw it, that's all. It will give me my value, 0.9977, but it just won't draw it. Both methods will give you the correct answer, though. Okay, that's it for calculating the normalCDF, the normalPDF graph, and the inverse normal. You've reached the end of this lesson.